This section is about transfer learning for LLM careers, specifically how fine-tuning and parameter-efficient methods like PEFT become practical career assets. It's not just about knowing the techniques, it's about showing employers you can adapt models efficiently, work within real-world constraints, and deliver measurable results. Framed the right way, those skills strengthen your AI engineering profile, open up LLM-focused roles, and make your portfolio much more compelling. Here's the core shift. In real-world AI systems, we almost never train models from scratch. Instead, we start with pre-trained models that already contain useful representations, then adapt them to the task we care about. That means less data, less compute, and much faster results. And that's exactly why employers care. Being able to fine-tune foundation models efficiently is now a practical production skill, not just a theoretical concept. This slide highlights where transfer learning shows up in the LLM stack. Supervised fine-tuning trains the model on example input-output pairs so it learns the behavior we want. Domain adaptation pushes the model toward expertise in a specific area, like law or medicine. Instruction tuning makes responses more consistent and better at following prompts. And PEFT, or parameter-efficient fine-tuning, adapts the model efficiently without updating every parameter. Here's the fine-tuning workflow in the order interviewers expect to hear it. First, choose the right base model for the task. Next, define the behavior you want the model to learn. Then, prepare high-quality training data that reflects that behavior. After that, run the fine-tuning job. Finally, evaluate the results and iterate based on measurable performance improvements. That sequence shows a clear, practical understanding of how fine-tuning actually works. Here's the key distinction. Full fine-tuning updates every parameter in the model, which gives maximum flexibility but comes with high compute, storage, and GPU cost. PEFT, by contrast, updates only a small subset of parameters through lightweight adapters, making it much more practical on limited hardware. In real product settings, the important judgment is choosing the lightest approach that still meets the requirement. Transfer learning is economically attractive because it dramatically lowers the resources needed to build useful models. Instead of training from scratch, fine-tuning often needs around 10 times less data. It also cuts compute costs, since PEFT adapters can run on a single consumer GPU. And maybe most importantly, it speeds up iteration, letting teams adapt, test, and improve models in hours instead of waiting weeks. Here's the framing I'd use in an interview. Start with prompt engineering and only move to fine-tuning when it clearly earns the extra cost and complexity. First, craft a strong initial prompt and evaluate whether the output is good enough. If it is, ship or keep iterating on prompts. If you need higher reliability, stricter formatting, or consistent domain-specific behavior, that's when fine-tuning becomes the justified next step. The first practical skill is data design. Start with strong prompt response pairs so the model sees clear examples of the behavior you want. Then define what correct looks like in concrete terms, not vague guidelines. Document labeling rules and edge cases so the dataset stays consistent across examples. And finally, do failure analysis. Look at where outputs break down and fix the data itself, not just the training script. The second practical skill is knowing the tooling stack behind modern model work. At the core are libraries like transformers, datasets, and PyTorch. Then you have the adaptation layer with tools like PEFT and Accelerate that make fine-tuning and scaling manageable. On top of that, evaluation and operations matter too. Things like experiment tracking and the Hugging Face Hub. Even on managed platforms, fluency here shows you understand the mechanics, not just the API. A strong portfolio focuses on narrow, measurable problems. For example, you might fine-tune a model to generate JSON summaries in a strict schema, classify documents for a specific domain, or improve a coding assistant's adherence to an internal style guide. What matters most is not how flashy the use case sounds, but how clearly you evaluate it. Show the baseline, explain the method and data, and report the measured result. Here's the pattern strong projects follow. Compare 3 approaches on the same task and justify the choice. Prompting only is the fastest. Lowest cost baseline when no training is needed. Supervised fine-tuning makes sense when you need a reliable style or output format, and dataset quality becomes critical. PEFT-based fine-tuning fits when budget is tight, but the model is large. The goal is engineering judgment, choosing the right tool, not just using every tool. This slide shows the engineering loop we use to improve model performance. First, we define the right metric for the task, whether that's F1 score, schema validity, or exact match. Then, we train and adapt the model using the selected fine-tuning approach. Next, we evaluate results against both a baseline and our target goal. If performance still falls short, we refine the data or adjust parameters and repeat the cycle. For interviews, be ready to answer 4 core questions. First, why didn't you train from scratch? Be honest about data, compute, and timeline limits. Second, why did you choose that base model? Show that you compared real alternatives. Third, what metric did you optimize, and why does it matter for the product? And finally, was fine-tuning actually better than prompting? Bring evidence, not just a gut feeling. A useful mental model here is freeze versus update. If the task is close to what the model already learned in pre-training, you freeze most of the weights and adapt lightly with methods like PEFT or LARA. That's efficient and lowers the risk of catastrophic forgetting. But if you need a real behavioral shift, it makes sense to update more of the model, or even fully fine-tune. This idea comes from computer vision and transfers cleanly to LLMs. An ideal public portfolio artifact has 4 pieces. First, a dataset card that explains GR data sources, design choices, and labeling rules. Second, a training config so someone else can reproduce your setup and hyperparameters. Third, an evaluation notebook that compares the baseline and adapted model with clear metrics. And fourth, published weights on Hugging Face, so reviewers can inspect and verify what you built. Across the ecosystem, the guidance is remarkably consistent. AWS emphasizes efficiency, lower data needs, and reduced compute. PyTorch recommends starting with a pre-trained model, since training from scratch is rarely practical. Hugging Face highlights PEFT as a way to adapt large models on limited hardware, and OpenAI frames fine-tuning as an iterative engineering loop. If results aren't good enough, improve the data and refine again. What makes a strong transfer learning hiring story is the combination of 3 things. First, technical judgment, choosing the right base model, adaptation method, and constraints for the problem. Second, tooling fluency, being comfortable with the actual production stack, not just the theory. And third, measurable outcomes, showing the baseline, what was changed, and the improvement achieved. Together, those elements make the work credible, practical, and easy to evaluate. Transfer learning is really proof of work. What matters is not memorizing definitions, but showing that you can make good decisions. Pick the right base model, prepare strong example data, adapt the model efficiently, and then test whether it actually improves performance on a real task. In practice, success comes from evidence that your adapted system works better where it counts. Here's the practical next step. Build one focused project with a narrow use case, a clear evaluation plan, and something you can publish. On that same task, compare 3 approaches: prompting, supervised fine-tuning, and PEFT. Then publish the full package, your dataset card, config, notebook, and adapter weights on the hub. Most importantly, practice explaining the trade-offs so you can justify every decision with evidence. Transfer learning is the default way we adapt modern models. In most cases, the capability is already there in the pre-trained model, so the real task is to tailor it to your use case in a responsible, efficient, and measurable way. That can mean full fine-tuning or lighter weight PEFT methods. And just as important, especially for your portfolio and LLM career, is being able to clearly document what you changed and why.